Hey guys, it's your favorite reliability test guy here with another fun-filled, action-packed video on reliability test and validation topics. This current video is an introduction to temperature humidity testing. I hope you enjoy these videos, and if you do, don't forget to hit that like button and subscribe to my channel. Thanks for watching, and let's get started. In this video, we will go over an introduction to temperature humidity testing. Phew, it's hot and sticky today. I'm sweating profusely, and the sweat is just running down my skin and won't go away. Why? Because the air is saturated with moisture, which we call humidity. The sweat that is produced by my skin pores does not evaporate into the air, as the air surrounding me is fully saturated with moisture or water vapors. This is why a 27 degrees Celsius day in California can be quite pleasant, or at least tolerable, while a day in Florida at 27 degrees Celsius can feel like you are in a much higher temperature climate because your body uses evaporation of sweat to cool down. In this video, we will cover definitions, what is temperature humidity testing, types of humidity tests, humidity test chambers, and humidity test execution. Below is a high-level summary that highlights the process from requirements to test results and test reporting. In this video, we will cover a topic on test execution and cover temperature humidity testing. Let's cover some of the definitions now before we dive into humidity testing. What is humidity? Humidity is used to express the amount of moisture or water vapor that is in the air for a particular location or even inside of a room. A common unit of measurement is relative humidity, or RH. I define RH in very basic terms. Some of you may say this is not a technical enough of a description, and I leave out terms such as absolute humidity. However, this definition is just perfect for understanding relative humidity for this topic on temperature humidity testing. So we will define relative humidity as the current amount of moisture or humidity in the air versus the potential maximum amount of moisture in the air for a certain temperature. Relative humidity is expressed on a scale from 0% relative humidity to 100% relative humidity. Let's watch a quick animation on why RH is a useful measurement tool for determining water vapor content in the air. Notice the RH of the air is currently at 50% RH. Let's go ahead and see what happens when we start introducing more water vapor into the air. As you can see, as we introduce more water vapor into the air, the relative humidity of the air increases until we reach 100% RH. So what happens when we try to add more water vapors into the air after the air is fully saturated with moisture at 100% relative humidity? Recall the sweat analogy we used at the beginning of this video. Remember that instead of the sweat being able to escape the body because of the high moisture content in the air, instead of evaporating, the water remains on the skin and pulls and drips and slides down our skin. Likewise, additional water vapor will begin to collect on surfaces and can even begin to pool dependent on the amount of water vapor that continues to be generated after the air has become fully saturated. Speaking of saturation, let's go ahead and define another term used for expressing the moisture content in the air, called the dew point. Dew point is a more accurate description of how we feel when we get sweaty and sticky. A lot of people confuse dew point with relative humidity, so let's define and clarify this term. Dew point is the stage at which water vapor will condense at the same rate as water in its liquid state evaporates. What this means is that as your skin is evaporating water, the moisture content in the air is condensing just as fast, which makes your sweat stick and make you feel awful, just like how you would feel after getting a tattoo after a night of binge drinking tequila. So, a quick way to think about the difference between dew point and relative humidity is dew point is the point at which the air is fully saturated with water and is condensing at the same rate as liquid water is condensing, while relative humidity tells us how close we are to fully saturated air on a scale from 0 to 100% RH. On the right, you can see a graph that demonstrates the relationship between dew point, temperature, and relative humidity. In the graph example, you can see that at 37 degrees Fahrenheit, that the dew point has been reached and relative humidity is 100%. However, take a look as you go higher in temperature. Notice that in this example, the dew point begins to drop, which signifies that the dew point is lower than the ambient temperature, which results in a decrease of the relative humidity of where the humidity level is compared to its maximum saturation point of 100% RH. This is a good thing from a comfort standpoint. In this example, as dew point lower than the ambient air temperature will leave you feeling more comfortable and less sticky. This is not always the case in the real world, however. As with places like Florida, there is a lot of liquid water sitting around, just waiting to get evaporated. And as air temperature increases, its ability to hold moisture increases as well, which makes you feel all wet and sticky. Likewise, notice that the dew point in this example increases as the temperature decreases. Relative humidity remains at 100% relative humidity at this example from 37 degrees Fahrenheit all the way down to 0 degrees Fahrenheit. While high humidity in the summer makes you feel hot and sticky, high humidity at cooler temperatures will make you feel more cold. The reason for this is that water is a better heat transfer medium than air. So when you are wearing your finest winter clothes, the moisture is wicked into your clothes and acts as a conduit between your skin and the surrounding moist air, which expedites heat loss from your body. Let's go ahead and define what humidity testing is now. Phew, I'm really working up a sweat with all this talk about humidity. Look at me just dripping perspiration in the picture over to the right. Okay, back on track now. So what is humidity testing? Humidity testing assesses materials and systems' resistance or robustness against water vapor in the surrounding air. Humidity testing is used for real-world simulations as water vapor occurs naturally all around us. An extreme example of this is the rainforest photo below, where we can physically see the water vapor in the air. Humidity can also come from man-made sources as well. Some examples include a rainstorm followed by direct sunlight, which evaporates the rainwater. Talk about a serious sauna going on there. Large bodies of water and high temperatures also produce water vapor in the air. And for a man-made example, a day spa, which will have either a wet sauna, a steam room, or both, produces water vapors into the air. So why is humidity testing important? Well, because it's all around us. You may not feel it due to a low dew point, but it's there. If you have one of those digital thermometers, they typically measure relative humidity. To the right is a digital temperature meter that I have in my lab. For me, 71 degrees Fahrenheit or 22 degrees Celsius at 54% relative humidity feels quite comfortable as pictured. But we aren't trying to run our product through perfect California weather conditions. No, in fact, we are using humidity testing to test for humidity extremes, the worst of what nature can throw at our system or product, where humidity-induced failure modes occur, including temperature and humidity testing can bring out failure modes such as corrosion, degradation of materials from temperature and high humidity exposure, exposed poor sealant designs, and electrical faults such as shorting. In regards to sealant, moisture, especially water vapor, can be a sneaky little devil, and what you think is a great sealant strategy may still be an opportunity for water vapors to creep into the internal cavity of your system. So now we know that high humidity can wreak havoc on our systems or products, but how about low humidity? It can also be a troublemaker as well. Low humidity levels create the ideal conditions for higher electrostatic discharges to occur. Electrostatic discharge, or ESD, typically occurs when a person becomes positively charged and comes within close proximity of an object that has some level of negative charge. The electrons from the negatively charged object flow to the positively charged person until the positive and negative charges balance out and come to equilibrium. The amount of potential is typically in the kilovolt range and can get as high as 100 kilovolts, depending on how few electrons are left on your skin and hair and how many electrons are stored in the negatively charged surface you make contact with. You can still have ESD events at relative humidity levels of around 40 to 60%. However, the added moisture content in the air allows charges to flow from an object to a positively charged ground through the air, reducing the discharge energy that flows between a person or object to another object as the capacitor is slowly discharged through the moisture in the air. ESD can be a killer in electronics, and I will be dedicating a video to ESD testing later on in this series, with more details on the physics of ESD and how to perform ESD testing. Additionally, low humidity, especially when combined with ultraviolet light, can cause materials to dry and crack, which can be cosmetic damage at a minimum, or even cause your system to lose its functionality, sealing, and can even cause safety issues. Let's go ahead and cover some of the types of humidity tests that companies perform. The first type of test is high temperature and high humidity. You have non-condensing and condensing humidity tests. A non-condensing humidity test is pretty self-explanatory, as it indicates that the water vapors are not allowed to condense on your test samples. A condensing humidity test is where you might need to get a little creative and put your engineering brain to good use, as the strategy here is to get the water vapors in the air to condense on your test sample. There are many different ways to pull off a condensing test, including attaching a cold plate to your test sample or building a chamber within a humidity test chamber. High temperature and high humidity tests are great for assessing corrosion effects on metallic materials, adhesion, and performance of adhesives against high temperature, high humidity environments, and even the impact of high temperature and high humidity on coatings. Another type of humidity test is high temperature and high humidity cycling, which is a high temperature and high humidity cycle that is then combined with an uncontrolled humidity low temperature cycle. This is a great test as you can cause materials to expand and then contract, which can create a diaphragm action, which may cause moisture to get pulled in through a pore sealing design into the cavity of your enclosed system as the materials begin to contract with the reduction of temperature. The image to the right illustrates a diaphragm pump, which demonstrates the diaphragm pumping action that I'm referring to with the contraction and expansion of a pore seal design. So keep this in mind when planning and designing your sealing strategy. Additionally, if the low temperature portion of the cycle is below freezing, you can evaluate the impact of what happens to a component of your system as the temperature decreases and water condenses on your system and then freezes. This can cause cracking and degradation of different parts of your system and is a great test to keep in mind for assessing humidity and freezing temperature environments. The next type of test is a low humidity and high temperature test. This test simulates an arid desert environment. Low humidity, as we discussed in the previous slide, creates a perfect environment for static electricity, which can wreak havoc on unprotected sensitive electronic components. Additionally, you can add a UV bulb to the chamber to accelerate drying and cracking of materials, as with dry rot that occurs with rubbers and vinyls. This testing can be accomplished with a humidity chamber that has a dehumidification coil, which is basically a small evaporator that captures and condenses moisture from the air. Additionally, you can accomplish this as well with a pure compressed air source to reduce the relative humidity in the chamber to an even lower dew point. Likewise, a low temperature and low humidity test simulates colder, drier climates that occur in the winter, which can also be used to assess resistance of the system to static electricity and cold temperature environments. Another type of test is the low temperature and low humidity test, which I do not recommend running with a conventional humidity test chamber. If you're trying to create snow here, get creative and go buy a snow machine and use a freezer. Don't try to run high humidity and low temperature in a temperature humidity chamber, as you can damage or incapacitate your temperature humidity chamber. So don't be an idiot. The final example is reliability testing. This is either a long-duration high temperature or high humidity exposure, or a test ran with a temperature and humidity levels higher than the expected worst-case environment that your system or product will encounter in the field or in customers' usage. You can accelerate temperature humidity tests just like temperature testing or vibration testing by using an acceleration factor. You can apply your knowledge or assumption on the field life and temperature humidity environment using the Arrhenius-Peck model to produce and come up with an acceleration factor. However, you need to be careful when creating an accelerated test, and we will go over this in a future video on acceleration factors and their application for reliability testing. In the magical world of humidity testing, the go-to test equipment used is a humidity test chamber, or temperature humidity chamber. As pictured, the outside of a temperature humidity chamber looks a lot like the run-of-the-mill temperature chamber. However, there is a few internal components that are added to a temperature chamber to produce high and low humidity environments inside of the chamber. To produce the high humidity levels, chamber manufacturers add what is called a steam generator. A steam generator typically has an internal heater that generates the steam or water vapor which is pushed into the chamber using forced air to push the moisture into the chamber. A steam generator can also use mechanical components and a heater to push the moisture into the chamber as well. As previously discussed, dry humidity environments are produced using a dehumidification coil, or it can be accomplished or complemented by using dry purge to displace and push out moisture inside of the chamber by creating a positive pressure inside of the chamber. Let's go ahead and take a look at two examples of high temperature, high humidity testing. The first graph demonstrates a high temperature and high humidity cycling test. As you can see, the humidity is held constant in the graph profile. However, most test standards that cover temperature humidity cycling allow for a certain percentage of tolerance for humidity drop, as the relative humidity will most certainly drop to some extent as the temperature is decreased in the chamber. The second example is a temperature humidity steady state test. This is typically used for reliability testing or shipping and storage testing to assess long-term effects and impacts of high temperature and high humidity on a system or product. Let's go ahead and discuss some pointers when performing humidity testing. The first thing you need to consider is to verify that your temperature chamber and humidity sensor are calibrated. Accuracy is important in the world of testing and measurement, so don't be like some places I've seen and have the original calibration sticker from the chamber OEM when you first purchased your equipment 5 years ago. Keep your equipment calibration up to date to ensure accuracy of your temperature and humidity measurements. The second thing to consider is the type of humidity sensing device that is inside of your chamber. Does your chamber have an electronic humidity sensor or a wet and dry bulb sensor? Electronic sensors are pretty easy. You just need to make sure that it is calibrated and that it actually works. Wet-dry bulb sensors, on the other hand, require maintenance. As pictured, the wet bulb has a wick that will need to be periodically replaced to ensure accuracy of your relative humidity measurements. So be sure to include wick replacements in your preventative maintenance schedule. But also be sure to inspect the wick periodically to ensure that it does not need to be replaced. You also need to make sure that your chamber is sealed as best as you can get it. Make sure to have port plugs installed so you slow down the loss of moisture from inside of your chamber into your test lab space. Even better, if you aren't going to run cables through your port plugs, install a cover with a gasket to really get a good seal. Run your chamber for 24 hours as part of a pre-test checkout to ensure your temperature humidity chamber is working as expected before placing your test unit into the chamber. This is important to ensure you don't waste time when something goes awry with your chamber and dependent on the industry, and if this is some kind of production acceptance test before shipping to customers, you may even have to scrap the test units and use new ones, wasting both time and money and making you look like a total idiot in front of your boss. A quick note, you should always need to consider the water supply for your humidity chamber. If you have a RO or DI water from your facility constantly being supplied to the chamber, this is not an issue. But if your chamber has a tank that needs to be filled to maintain water supply to the steam generator for your humidity chamber, you need to have a periodic check in place to make sure you have water in the tank, or your chamber will abort the test and cause one of the issues mentioned in the 24-hour pre-test check pointer. Also, make sure you're using RO or reverse osmosis water, or DI, aka deionized water, as the water impurities in tap water can damage your chamber. Also consider safety factors as well. Don't have electrical cables sitting on the bottom of the chamber where condensation and water can accumulate, as you can cause shorting or even electrocute yourself or someone else who goes into the chamber to check on your test units. So don't be an idiot and play it safe. Some of the key takeaways from this humidity testing video are: determine the temperature and humidity environments that your system or product will encounter during its operational life. Predetermine failure modes that you are looking for or want to find or hope to avoid. Ensure your humidity test chamber is calibrated and operating as expected, and also verify your sensors are working and maintained. Don't mix water with electricity. Be smart and play it safe. If you need help tailoring a humidity test to your system or product, or selecting an industry-specific standard and test, feel free to reach out to me at one of the links in the description. Also, if you would like more advanced training or even hands-on training at your lab for temperature humidity testing, please feel free to reach out to me as well. Hey guys, thanks for watching this video. I hope it was as fun for you to watch as it was for me to make. If you have any questions or comments, feel free to reach out to me at one of the links below. Thanks for watching and have a great day.